So today we're going to start section 2.1, and in chapter 1, what we actually looked at was a bunch of different types of equations and how to solve them. So we're going to sort of focus our attention in a little bit more specifically to a specific type of equation, in section 2.1, and those are going to be functions, and this is going to be most of chapter 2 that we're going to be working with functions. So to start with, a function is a rule that assigns each element in one set to a unique element in a second set. So it talks about the first set, or one set, and a second set right here. The input is the first set. Your output is your second set. So we use the phrase inputs and outputs, and that's good phrasing. There's some other terminology that we use for these. We use the phrases independent variable and dependent variable. Your independent variable is another name for your input. It's often the x value from what we are given, because we use a lot of x's and y's, right? It's this x. And we'll talk later on today, too, that when we have a function, these x values compose something called the domain. The dependent variable is your output. It's your y values, typically. And we refer to this when we have a function as the range. So I'm going to do an example, but I want to change maybe a little bit of the phrasing of it because I really confused my first class, because I get the feeling that nobody in there has ever been to the post office before. And so the question didn't really make a lot of sense. So I want to take the same example, but just change the thought of it a little bit, and maybe it'll help. That's what I'm hoping for. So you guys are my guinea pigs on try number 2 with the same example. All right, so who's bought something online before? Raise your hand. Okay, so let's pretend you're buying something online as opposed to the post office, and we'll see if we can make this work. So our example is we're trying to mail something. You can ignore the fact that it's a letter. It's really quite irrelevant that it's a letter or that it's something else. You're buying something online. All right, and there's a weight of the item you're buying. Agreed? And there's a price that it costs you to ship or mail or whatever kind of terminology you want to use to get that item to you. So in our house, we do a lot of Amazon. That's our thing. I think I bought almost all my kids' Christmas presents on Amazon this year. Super easy. So, but most shipping places have the same sort of a process that Amazon or the post office does. You get to the end and you have to select a shipping option, right? And not always, but a lot of times there's more than one option. Agreed? Sometimes it depends on how fast it gets there. That's a lot of times what it is. Sometimes it depends on how you send it. Do you send it with UPS or FedEx or the post office, depending on what kind of shipping options that company or that organization uses? So this question is actually asking you whether or not things are a function of one another. So we have our item that we're trying to mail, and it has a specific weight, W. And the question is whether the cost to mail it is a function of its weight. So we're going back to this idea of function as defined over here. A function is defined if we have a single output for the input value. So the first part of this question says, is the cost a function of the weight? Do you have only one cost possible for the weight of your object? And the answer would be no. They give you options, right? Do you want to ship it with FedEx? Do you want to ship it overnight? Do you want it key delivered to your door or inside your garage, or whatever options they have at their organization? They give you choices. Are you tracking with me? So it's not a function because you have more than one option of cost given the weight of your object. Does that make sense? So the first question right here, if we kind of subscripted it A, is C a function of W, right? Is the cost a function of weight? The answer is no. And this works at the post office too, which is how the question's actually worded. You take a letter to the post office, you can still overnight it. Okay, so even if you just limit yourself to one specific, carrier, namely USPS, they give you options too. Do you want it overnighted? Do you want it second day delivery? Do you want it priority shipping? Right? Lots of different options for your package or your letter. So this is no, because there is more than one shipping cost option for your, in this case, it's a letter, but your package or whatever. So for your letter. The other question that it asks is for you to sort of flip it around. All right? Is W a function of C? So in other words, can you know for sure the weight of your object based on how much it costs you to ship it? So let's again think about doing it online, because I think that's a better connection for you guys than my post office problem. So when you get to the end and you have one item, maybe it's one shirt in your basket, and somebody else has 3 items, right? Maybe 3 shirts in their basket. Is it possible that you are spending the same amount of money on your shipping?
Yes.
It is, right? In fact, it's quite possible. Usually they sort of kind of group together things, and if you have a certain price, up to a certain price, they'll ship it at a certain rate. Or sometimes it is a certain weight, but the weights can be different, and it costs you the same amount. So it's not a function the other direction either. So this is no, because a single shipping cost I'm going to use the word ship. A single cost to ship the letter could have several different weights. And again, this is exactly how it works if you take it to the post office. So if I have a letter and it has, like, imagine I actually wrote a letter. Nobody does this anymore, but you actually wrote a letter to your grandma. And I wrote the letter and it had 1 paper inside of it. And my sister wrote a letter and she had 3 pages inside of it. As long as my letter and her letter both weigh under 1 ounce, it still costs me 1 stamp to mail it. It's the same price, no difference in cost. There's always a range when you're looking at actually just the weight when you go to the post office. If it's between this weight and this weight, it's this price. So that happens sometimes with cost. So if it's between this cost and this cost, it's this price. You probably have seen things before where they'll say something like, if you buy at least $50, the shipping's free. You'll know what I'm talking about, right? But there's a different cost if it's below $50. It's the same idea. So neither of these are functions the way that this problem is set up. So the answer to the actual question, after considering these, is neither. Neither one of these is a function of the other one. Now, let me give you just a verbal example of one that is a function, because I also don't have that written into your notes. So let's say, for example, that you talk about an individual family, and I'll just use my family for an example, because I've talked a little bit about my family. You guys know that I have several children. So if you take an example as one of my children living in my house, right, and you ask them, and I know this sounds sort of funny, so we're going to limit it to the fact that we're going to limit it to the fact that they call me mom and they call my husband dad, because I know we've got some adoption foster care stuff, and so they actually, some of them do have other moms and other dads because of the dynamics of our situation. But in most dynamic situations, that's not the case, I know. So if you asked my child how many moms they have, like people that they represent and they understand and they recognize as mom, every single one of them would give you 1 answer, right? They wouldn't give you 2 answers in my house. And you could at least talk about their biological mom. You could do it that way if you want to, too. Every child has exactly 1 biological mom. So let's do it that way. That might be easier, right? Every single one of you, exactly 1 biological mom, okay? But if you took a mom, you could not reverse the situation and say every mom has exactly 1 biological child, right? That's not a function in that direction, So it's a function in one direction, right? The child has exactly one biological mother, but it's not a function if you go the other way around. Okay, so that's a verbal example and a non-example. So it doesn't always end up neither on both of them. In the United States, anyway, you could do an example as well. We'll do a husband-wife example. Because we have laws that represent that you can only have one spouse legally on paper, right? Like that's real. You can only be married to one person at a time. So if you asked a wife, does she have only one husband? The answer would be yes. And if you have a husband, they have only one wife, the answer would be yes. So it would actually work in both directions.
Oh.
So when we're working with these problems, sometimes they don't work in either direction. That's the example we talked about here, right? The one with the postage, basically. It doesn't work in either direction. Neither one's a function of each other, the weight and the cost. But you do have situations where it works in one direction and not the other. That's the biological mom with the child or multiple children, right? It works one direction and not the other. But sometimes things work both directions too. And a husband-wife would be a verbal description of one that works in both directions. Each one is a function of the other one. Okay? So a verbal description is one way to talk about functions. A second way to talk about functions is graphs. People like graphs for some reason. I think it's just this idea of I can see it a little bit more directly instead of reason through it. So you've probably seen the vertical line test before. I'm not going to ask you to tell me what it is, but it probably is a phrase that you're like, oh, yeah, I remember we talked about that once upon a time. So the vertical line test is a visual way of describing whether or not a equation, typically associated with an equation, satisfies the conditions of being a function. So I'm going to draw 3 different graphs. This is what they would look like already on your, homework or whatever. So this is my first graph. So just sketch that in there. Here's my second one. And then here's my third one. So the vertical line test says that I can drop vertical lines through my graph. And if when I do that, I never cross the graph more than once, then it's a function. So the graph that I just dropped these vertical lines through, and I only dropped a few of them, but you could imagine dropping sort of infinitely many vertical lines here, right? Would it ever cross the graph twice or more? No. Each line crosses the graph one time. So this is a function. So how does that sort of go back to the definition of function? Why is that sufficient? Well, the definition of function says that each input, right, each x value has only one y value. Well, when I drop these vertical lines, I'm dropping them at the x values. So if it's only crossing it one time, then it only crosses the x value one time, giving you an output of a y value one time. Every one of these points represents an xy ordered pair that is unique to that x value. All right, it doesn't have 2 y values there. It has only one x value or one y value for that x value. It's different if I try to drop them into to example B. So no matter where I drop these in example B, many places anyway, I cross the graph twice. So again, why is that failing this to be a function? Well, because at this particular x value, let's use blue, I have 2 y values. So these 2 ordered pairs have the same x value and different y values. That's exactly what you can't have in order for it to be a function. You can't have the same x value and different y values. We'll get to that in a little bit later. You can't have the same x value and different y values. If you do, then it's not a function. What about on the last one? Function or not a function? It's not a function. Because I can find at least one, and in this example too, just like the last one, lots of them, where they cross the graph twice. And anytime a vertical line crosses the graph twice, it fails the vertical line test, which means it's not a function. Okay? So we've talked about a verbal description. We've talked about a graphical description. I'd like to look at another example where our possibility of functions is represented by ordered pairs. Anytime we have a collection of ordered pairs, it's actually called a relation. So a relation is any set of ordered pairs. So these are relations that I'm being given. And we're trying to decide if they determine a function. And I'm going to show that to you in actually 3 different ways of how you make that decision. So one way you can make that decision is that you can actually graph them. Okay? So like if you plotted these on the number line, right, or on the Cartesian coordinate plane, the xy ordered pairs, right? If you plotted them and you dropped your vertical lines, you could do it just like you did over here. So I'm not going to do that, but that's what you could do. So if you really like the vertical line test and you just want to plot the points and drop lines, fabulous. And you can make the same assertion that we did before. Yes, it is. No, it isn't. A second way that you can do it is you can analyze the values that are given. For example, if I looked at the x value of 1, how many y values are associated with an x value of 1? Just 1, the number 7. How about the x value of 0? Well, just 1. It happens to, again, be the number 7, but that's not a problem. The x value of 0 has 1 corresponding output, y, 7. How about the x value of 4? 1 output, 6. How about the x value of 9? 1 output, 6. So this is a function. Now I'd like to rerun that same thought process for the other example, and then I'll go back and show you a third way of thinking about it. What about the x value of 7? It's got the y value of 1 and the y value of 0 associated with it, right? And if that weren't enough, the same thing happens over here with the x value of 6, doesn't it? The x value of 6 has the y value of 4 and the y value of 9 associated with it. There are 2 outputs for at least one of my inputs, in this case both of them. So this is not a function. Okay, I'm going to show you one more visual way to look at this, but it's not a graph. So what we're going to do is we're just going to separate our inputs and our outputs. So there's my input, here's my output, and put items in the categories. So all the inputs are all the x values. So I have 1 and 0 and, let's see, 4 and 9. Those are my inputs, right? And then my outputs are just 7 and 6. So I'm just making a collection of them. It's like I'm throwing them in a bucket. And then I'm sort of pairing them up. So the number 1 goes to the output of 7. The number 0 goes to the output of 7. The number 4 goes to the output of 6, and the number 9 goes to the output of 6. You'll notice each of my input values has only one arrow that's leading out and corresponding to something. That's what we're looking for it to be a function. If you try this process again with the second example, which is actually just the flip of the first one, the inputs are just 7 and 6. My outputs are 0 and 1 and 4 and 9. The number of 7 goes to the number 0 and it goes to the number 1. The number 6 goes to the number 4 and to the number 9. That can't happen and it be a function. Yes, ma'am? You could, yeah. So it would be another visual representation, sure. So anytime the input has 2 arrows exiting, going to 2 different locations, it's not a function. So it doesn't matter to me which of those 3 options, right? Plotting them on an XY ordered pair, sort of reasoning it out the way we did initially earlier on, or drawing these kinds of a charts or something equivalent. It doesn't matter. But they will all yield the same answer when you're done. Is it a function or is it not a function? All right. Now I mentioned earlier on that one of the other things that we would hit today at the very end here is actually domain and range. Domain are my x values, range are my y values. Okay? So we already mentioned that. I'll just write it here again. X and y is how we tend to see them most frequently. So we're going to go back and we're going to do a couple of examples that we saw earlier that were already functions. Notice we can't talk about domain and range if we have things that are not functions anyway. So we're only going back to the examples that we said were functions. Otherwise, it doesn't make any sense. So we're going to go back to example 2a, which was our picture right here. So there's lots of ways that you could potentially think about domain and range. If it's something that you feel like you're really good at and you don't like my way of doing it, then don't do it my way. That's fine. But I am personally a very visual learner. So images, when I memorize, like passwords and things like that, locations where the numbers are on the keypad, that's how my mind thinks. So I think very visually. So when I think about domain and range, domain being the x values, I want you to imagine that you're on this graph, but you're on the x-axis, and you're walking, okay? So we walk from left to right, just like we read. So we'll start from the left-hand side, and we will begin walking. And as we're walking, we're looking up, and we're looking down. And every time when we look up and we look down, if we see part of the graph, that's the white part that I drew in originally, those are values that are in the domain. So on this graph, no matter how far left I start and look up or down, in this case down on this graph, I have part of the graph. Right? There's still a value there. Because this value plummets forever. It will continue to go down forever and go to the left forever. And as I keep walking and keep going up and down and up and down, I'm always able to do that on this entire graph, no matter how far left I go to how far right I go. There's always values that I see as I look up and down. So my domain for this is all of it. It's negative infinity to infinity because I can start from the very far left, I can go to the very far right. Now, this isn't an example, but let's imagine my second graph, just for the sake of argument for the moment, with the bottom half removed. If I did this, I would have a function, right? I would. And if I do this one, I actually have a place where I don't have any values, right? Beyond this part of the semicircle to the left, there aren't values. There's actually a starting spot and an ending spot on this graph, whereas my graph on part A didn't have that. Now let's talk about range. Range is y values. So very much like I'd like to walk along the x-axis, when I'm talking about range, I'd like to climb up the y-axis. So we start forever down here, as far as we can go down, right? Climbing. And instead of looking up and down, the way I was with domain, I look left and right. So I'm climbing up my y-axis, and I'm looking to the left, and I'm looking to the right. Some of the time, I see one value. Some of the time, I see two values. But no matter where I am climbing up my y-axis, I always see a value one direction or the other or both. Correct? So again, as I'm climbing up, no matter how far down I start and no matter how far up I go, I always have y values. So my range is the same, negative infinity to infinity.
That's for the first one, right?
Yep, we're still doing example number 5, which is 2a. Yeah. On the half circle, because that's where I was going to talk next, actually, if I start here sort of at the bottom of my visual on the screen, I don't have any y values if I look left and right. There's no part of my circle, right? I keep looking left and the right, but until I get all the way up to the x value, or the x-axis, which is the y value of 0, I don't have anything. So this one starts at 0, right? That's the first place I look left and right and see values. And it will end at whatever the peak is of that circle. I don't have it marked with an axis or with a grid or anything, but there is an ending point. It doesn't go to infinity like part A does. Okay? So that's how to think about it from the graph's perspective. 3a was also a function. So domain is my x values, range is my y values, which means ordered pairs are really easy to do this for. It's just a list. List of the x values and a list of the y values. So my domain, it's curly braces, and I just list the x values. If you want to list them in order, you can. It doesn't really matter, but you don't duplicate them. So if I just list them in the order they were presented, I would have 1, 0, 4, and 9. And I do the same thing for my range. My range is 6 and 7. In some order, either order 7 or 6, 6 or 7, doesn't matter. But I don't duplicate list them. Right? I don't list them twice. They're just listed one time. number 7, if you were looking at number 7, one option that you have is you have the option to actually put it into equation, into a calculator. I know some of you have graphing calculators. Not all of you do. And I'm going to show you 2 ways to do this problem. One option is to put it in your calculator, and if you do, you will actually get a graph, just so that we can all talk about it together, that will feel a lot like what we did on the circle example that I did before. So the graph, actually, put it up here. The graph will look like, I think it's like this. And it's right here at 5, that I know. So you could look at a graph, okay? That's fine. We can start from the left. We can work to the right. If we do, we would see that our domain gives us values that are starting at 5. And I actually can equal 5 because if I put it into the equation, 5 minus 5 is 0, and the square root of 0 is 0. That's fine. And as I keep walking to the right, I can continue walking to the right indefinitely. Now, if I'm climbing up the y-axis with this picture in mind, I know this looks sort of like it's like leveling off. That it's really slowly leveling, but it's not leveling off at 0, at a specific value. It keeps going down, just really slow. So no matter how far down I go, if I look far enough to that side of the graph, that positive side of the graph, I will see values. So my range is actually negative infinity as I'm climbing up. But there gets to be a point on the y-axis, on the x-axis when I hit y equals 0, where I don't have anything above it. Right? There is nothing on the top half of this graph. So it does stop at 0. And it actually equals 0, again, because when I put in x equal 5, and I did 5 minus 5 is 0, the square root of 0 is 0, that was a y value of 0. I have the ability to do that. Thinking about the equation, this will be the last thing. Thinking about the equation itself. The reason that the range makes sense is because what kind of values come out of square roots? I did it backwards. My graph is backwards. Oh, that's what happens when you don't put it in your calculator. Let's come back to this one next time. We'll start over with number 7, and we will fix that one when I did it, because I did it my graph backwards. So sorry.
For 7?
Yeah. I didn't do 7 in class in the other one, so we didn't get that far. We'll start with 7 next time. Have a great couple days. I'll see you guys on Thursday.